Okay, last lecture of part 3, we're going to do a quick recap on confounding, just because it is so important for you to understand the concept of confounding when doing observational studies, which is probably the most common study design used in medical research. Okay, as always, let's start with an example. So, the factory workers of Art Smith are concerned about having severe shortness of breath, SOB. 100 employees exposed and 100 not exposed were selected from the workforce, and here is the table summarizing the results for SOB, right? So if you look at this as a classic contingency table, you have your disease yes, no, you have your toxin yes, no, so the presence of the toxin yes, no, you have your totals by row, okay, and then you have your percent SOB, right? So you have 38% when the toxin was present, 15% when the toxin was not present. You do a Fisher's exact test and you get significance, right? Here's your odds ratio and your relative risk. We'll have a little chat about that later, but here's your odds ratio is 3.48. Here's your confidence interval and your relative risk is 2.53. And here's your confidence interval. So far, pretty straightforward. Okay, let's review relative risk and odds ratio a little bit. So in medicine, you're always going to be talking relative risk and probabilities. That's your go-to, right? However, when you're doing statistics in medicine, you're probably going to end up with an odds ratio, and that's because there are just so many really powerful statistical methods that you can use in medical research that are going to yield an odds ratio. But in this case, we have a contingency table, so we can calculate both very simply. So let's do that. So a relative risk is the probability of getting the disease when you are exposed to the toxin over the probability of getting the disease when you are not exposed to the toxin. So in this case, it's going to be 0.38 over 0.15 gives you 2.53. Easy, right? Odds ratio, not as straightforward. So the odds ratio is going to be the probability of disease over the difference, Q, which of probability of not getting the disease, which is going to be 1 minus P1, right? So Q1 equals P1, 1 minus P1. So you do P1 over Q1 divided by the same for when you're not exposed. So the probability of disease when you're not exposed over Q0, Q naught, which is going to be 1 minus P naught, okay? And that is going to be, in this case, equal to 0.38 over 0.62 divided by 0.15 over 0.185. And you can see that we made the numbers here really easy for you to be able to just do these in your head. What do you end up with? 3.48. So you can see in this case the relative risk is not equal to the odds ratio. Sometimes it is, but most often it's not, and we'll talk about that in a little bit. So his friend John Smith was surprised because his workers are exposed to the same chemical and have reported no increase in SOB. He then remembered that most of his employees are women. Now, this observation led Art to look at the results for his female employees. So in this case, it's exposure and SOB percent in females. Okay, so we have disease yes, no, we have toxin yes, no, and if we look at the numbers, we have 10% have SOB when they're exposed and 8.7% have SOB when they're not exposed. Once again, we can calculate the odds ratio and the relative risk. In this case, interestingly, the odds ratio and the relative risk are very, very close. So Art now assumed the excess risk must be among his male workers and was surprised that his male workers experienced no increased risk with a p-value of 0.86. So if we look at the exposure and SOB disease in males, you just look at males, disease yes, no, toxin yes, no. If we look at the total SOB, you have 45% when exposed and 40% when not exposed. Fisher's exact show you that it's not significantly different. Your relative risk and odds ratio, very similar, though your odds ratio is a little bit bigger than your relative risk. So let's have a look at the percentage of SOB by toxin exposure and sex. So here you have females, here you have males. You have 2 out of 20, so 10% of females, 36 out of 80, so 45% males, right? Overall, when you combine them, it's 38 out of 100. Females is 7 out of 80, 8 out of 20 males, and with a total of 15 out of 100. So this is the data together that we saw in the first slide. The relative risk here is 114, 113. The overall is 253. Fisher's exact here, no difference, no difference. But overall, interestingly, there is a difference as we saw in the very first slide. Let's make sense of our results. So males are at a higher risk of disease. And there is a higher proportion of males exposed to the toxin. So the increased risk of SOB in the group of exposed workers is not due to the toxin, but because it has a greater percentage of males who have a higher percentage of SOB. So perhaps males are given dirtier jobs or choose not to wear protective clothing. So the sex variable is called a confounder. Now, before we move on, let me just point out, I was in the previous slides, I was showing to you that the relative risk and the odds ratio is not always equal, and they don't always represent the same thing. And we'll definitely talk about this in a later lecture. But what I wanted to point out is when the prevalence of the disease you're studying is very low, then the odds ratio and the relative risk are almost identical. When prevalence of the disease increases in your data set, then the gap between odds ratio and relative risk increases. So meaning that the odds ratio and the relative risk are not equal. Okay, last example. Let's talk about a famous discussion between Charles Darwin and his cousin Francis Galton, who both are known for their contributions to science in the late 1800s, early 1900s. So Darwin, concerned about small sample size of his experiment, and if you'll remember correctly, he loved to work with pea pods as well as flowers to look at inheritance. Now, as only a moderate number of crossed and self-fertilized plants were measured, it was of great importance to me to learn how far the averages were trustworthy. I therefore asked Mr. Galton, who has much experience in statistical researches, to examine some of my tables of measurement. Now, the typical survey in the social sciences in the 19th century was very large. So they would collect large samples and report the summary statistics. Now, Darwin, a biologist, understood that a difference between two means of only 15 subjects selected from two different countries would unlikely result in any sound conclusions because of the wide variability among the observations. So, however, Darwin believed the small sample size of his experiment was compensated by the care he took in the design and execution of his study. So he states, but the case is somewhat different with my crossed and self-fertilized plants, as they were of exactly the same age, were subjected from the first to last to the same conditions, and were descended from the same parents. Okay, let's create two data sets of paired data. Now we're using paired data because, as Darwin said, he was so meticulous in making sure that he was using the right plants for his studies that basically he was pairing them. And so that was the intent that he had, was to make sure that they were very closely paired. So we have two data sets, one called inbred, one called crossed. Now, when we create a paired data set, don't forget here we have what we call a wide data set, which means that data are in columns. And so in order to do that, we're merging the crossed and inbred data sets. As you can see here, I'm just getting my pointer. We're merging these two data sets. And then we're taking the difference between crossed and inbred. right? So this is, remember, this is a pairing, a paired data set. So if you were to print your data and put some summary statistics at the bottom, this is what it would look like. Okay, you're crossed your inbred data sets. Here are your pairs, 15 pairs. Here's the mean, the variance, and the skewedness of both data sets, and this is your difference. Okay, so of course we want to do some statistics, so we're going to compare the means using, in this case, we can use means or t-test as we've done previously. So here is your proc means. We're using the wide data set because the data is in columns. And we're going to ask for your mean, the t-test testing whether or not the mean is significantly different from 0, the probability, the confidence limit. Okay. Your variables, of course, the 3 variables, cross, inbred, and difference. Then we can do a t-test, but using the paired statement, which is saying that it's a paired data set and in columns, so wide. And then we're going to do proc correlation once again to look at whether or not these 2 variables are correlated or have a linear relationship. Okay, let's have a look at the output. So for the means procedure, of course, you're only going to look at the difference for when it's tested against 0. And you can see here the probability is 0.0497, so just barely significant with your confidence limits. This one actually including 0, but that's just a decimal. If this is actually less than 0.05, so this would not contain 0. So be careful with that. We just asked for 1 decimal, and that's the reason it looks like 0, but it's not. Okay, when we look at the proc core, so the correlation, do we find a correlation between crossed and inbred? Interestingly, we do not. So there is no correlation, no statistical correlation, statistically significant correlation between crossed and inbred. There is none. So that's interesting because he was saying, I basically paired these and I was so meticulous and cautious in putting them together that you would expect these to be linear, have a positive or negative linear relationship, but there's no relationship. Now, when we do the t-test of the paired result, of course, no surprise, we get the same result as when we did proc means for the test against 0, and we get the same p-value. Of course, you get a t-value instead here, 2.15, and here's the data that we're looking at. This is just an output from SAS that allows you to kind of have a look at the inbred versus crossed data sets. Okay, so now why don't we rerun all of that analysis, but ignoring the possible pairing? So we create the data sets once again, but this time it's going to be in the long format because we're not going to be pairing. We're not interested in having the data paired. Okay, let's look at the analysis assuming a completely randomized design. Now we do a t-test, of course. You guys are pros now. You know what's going on with the 2 independent sample t-test. First thing we do, we rush to the p-value. Yes, that's naughty, but let's do that anyway. And you'll see that, oh, look at that, 0.02. It is significant. Wow. Now, interestingly, what we'll also do is we'll keep scrolling down, and we see under equality of variances that the p-value is significant down here too, which means that when we tested for the equality of variances, we found a significant difference, which means that the variances are different. And if that's the case, we need to use the Satterthwaite test and not the pooled variance test, but the Satterthwaite. So this is the p-value you would report, 0.0233. So that's interesting that Darwin assumed paired data, but that was not the right thing, because it turns out that because his data was not correlated, that it was actually a hindrance. It was not a good thing for him to do a paired analysis when there's no correlation. It's actually better here to assume that the 2 samples are independent. And that is it for lecture 3 of part 3. And next up is part 4. And in the first lecture, we will be talking about categorical data.